So let's move on to the next algorithm, and this algorithm is a very popular algorithm in machine learning. Even today it is being used in a lot of companies. This or some variant of this algorithm that we will talk about is being used in all your all your favorite e-commerce or social media companies, right? So be it Facebook, Instagram, I'm sure Amazon, Flipkart, whatnot, right? So they use in their day-to-day machine learning application some variant of this algorithm that we are going to see now. It's a very powerful, a simple but a very powerful algorithm. Okay, so let's see what this algorithm is, right? So it's called the decision tree algorithm. So again, let's look at the same example that we had. Now we have, instead of 3, in this particular example, I have taken 4 data points, John, Mary, Smith and Susan, and then I still want to answer the question for Hari, right? So that's the thing. John and Mary were paid the loan back, whereas Smith and Susan didn't pay the loan back, and now I want a decision for Hari. And now this, as the name suggests, we are going to look at an algorithm which is going to make a decision using a tree, right? A tree is an object, as we will see, that will help us make decisions, right? So and I'll tell you what this tree is, right? So here is an example of a tree, and the tree has what are called as, why is it called a tree? Well, a typical tree grows like this, right? So this is the root of the tree, and then you have these branches, and the branches will have branches, and the branches will have branches, and so on and so forth, right? So now you can imagine this as an inverted tree. In computer science, at least, always the root is at the top. For whatever reasons, that's the standard convention that people follow, and it's intuitive in a causal perspective that we start from the top and then we make a series of decisions. This is what is called as the root of a tree. At the root of a tree, what you do is you ask a question. In this case, the question is the age less than 30? Now, for a new test data point, you ask this question, is the age of Hari less than 30? Well, in this case, Hari is 20 years old, so the answer is no. So if the answer is no, then sorry, the age is less than 30, the answer is yes, right? So is 28 years old. So in this case, the answer is yes. So this is the yes branch and this is the no branch. Now, if the answer was no, then the decision, so this is what is called as a leaf node, where a decision is made. No longer, you are asking questions. So if the age is greater than 30, then immediately you decide, go to a leaf node and you say, no, the loan cannot be granted. If the age is less than 30, which is what Hari's case is, then you ask a different question about a different feature. In this case, the question is the salary greater than $10,000? If the answer is yes, again you branch this side, and then the leaf node, you hit another leaf node, it says yes, the loan can be granted. If the answer is no, then it says no, the loan cannot be granted, right? So basically, what we have done is, from the data set, we have extracted out somehow, and we will talk about how, somehow we have extracted out a tree, and that tree is what we are calling as a decision tree. And what's the power of this decision tree is that once you have this decision tree extracted from the historical data, you don't need the historical data anymore. Now you can make predictions for new data points like Hari in this case by running through this decision tree, asking a series of questions about Hari which the tree asks, and based on the answer you take one or the other branch of the tree, and then eventually we will end up with a leaf node, and the leaf node will have a corresponding label whether it is yes or no. In this case, I first asked the question, is the age of Hari less than 30? Answer was yes. So then I went to the yes branch. I asked the question, is the salary greater than 10,000? The answer happens to be yes, and because Hari's salary is 16,000, and so I will decide to give the loan to Hari. Now, that's during the test time, right? So once you have the tree, it's easy to say how to make a decision for a new test data point. You ask this series of questions, you navigate the tree and you will hit a leaf node, as simple as that. The interesting question is, how do I arrive at this tree? That's the learning question. I have this historical data, and from this historical data, I somehow have to extract out this tree. And this tree, I hope, is the tree that best represents my historical data. And now once I have this tree, I can throw away the historical data and compare it with the k nearest neighbor algorithm, right? So now during test time, I don't need the historical data, I only need the tree. Whereas in k nearest neighbors, I need the historical data because I need to find who are the neighbors. And if you had 10 million data points, you have to make 10 million computations to figure out, or more than that, to figure out who the top k neighbors are. Here, none of that happens, right? So once the tree is built, I can throw away the historical data. I can use my test data point to run through the tree and make a decision. As I said, the interesting question is, how can I build this tree from the historical data? Now, to do that, again, that's a slightly involved procedure. We won't really go into the specific details of this procedure in this workshop, but I'll give you a high level overview, right? So the algorithm that is used to build this decision tree roughly has the following flavor, right? First, we want to decide who the root node is, right? So how can we decide that age less than 30 is the most interesting question to ask to make a decision? And to do that, what we do is we go through all feature comma threshold pairs, by which I mean, for instance, your feature can be age, your threshold can be 20, your feature can be age and your threshold can be 30, your feature can be salary and your threshold can be maybe $10,000, and so on and so forth, right? So for every feature there are multiple thresholds, and then you can ask the question, is the feature less than or equal to threshold, and see how good is that question for your data set. And there are some ways of measuring goodness of questions, using some measures of impurity, which we won't talk about in this course, but think of it as, which question gives me the most information among all possible questions. What is a good question? Let me at least tell you that much, right? So what's a good question? Well, if there was a question, right? So let's say we take, for this particular data set, we ask the question, is age less than 30? Now what is the use of this question, right? So in this data set, is age less than 30? Well, I ask this question to each of my points in my training data. Well, in this case, John, Mary and Susan have age less than 30, whereas Smith has age greater than 30. So if I ask age less than 30 as a question to my training data, those who say yes would be John, Mary and Susan, and those who say no would be Smith, right? And now what is John's label? John's label is yes. Mary's label is yes. Susan's label is no. Susan did not pay back, whereas John and Mary did. What about Smith? Smith's label is no. Now, this question is a good question because by asking this question, if the answer is no, then in my data set there is only one person who has answered this question as no, and that person's label is no. In other words, this is a very pure data set, right? So everybody on this side who answers no to this question has label the same label. In this case, the label also happens to be no. Whereas in this side, everybody who answers yes to this question, which is John, Mary and Susan, not everybody has the same label. So it's still somehow impure, right? So because there are two yes and one no. Now what I can do is that I can then further split this by asking a different question, which is in this case salary. Salary greater than 10,000. Well, for that salary question greater than 10,000, John and Mary would say yes, whereas Susan would say no, right? So which means that I further ask this question, and now I get John and Mary on one side and Susan on the other side. Now the label of both John and Mary is yes and yes, whereas the Susan is no, and so now this has also become a pure node, this has also become a pure node. Now basically what we are doing is, at every step what we are doing, we are asking questions such that we split our data set into two parts, and both these parts are as pure as possible. Now if there was a question, so maybe age less than some number or salary greater than some number, if there is a single question that I can ask such that it divides my historical data into two parts, such that on one part all the labels match, on the other part all the labels match. Now that would be the best possible question, because I can ask a single question and then I can decide whether the label is yes or no, because everybody in my data set who says yes to this question has the same label, and everybody who says no to this question has the same label. That's the best possible question, most informative question, because I can ask that question and then I can gain information about whether the label is yes or no. Now such a question may not exist. If you find such a question, you are done. You can ask that question and make your decision for your test data points also. But if you don't have such a question, then you kind of keep asking more and more questions depending on what is the data set that remains in each of these sites, and then splitting that further and further, right? So that's what I mean by saying find the most informative feature comma threshold. When I say feature comma threshold, the question you are asking is the feature less than or equal to the particular threshold? And now you split your data according to the chosen feature, like how we split the data 4 data points into 3 on one side and 1 on one side by asking the question age less than 30, and then in both sides you see if it's a pure data set. If it's a pure data set, that is if all the labels on this data set matches, you stop asking questions, otherwise you further refine this part of the data set by asking more questions. And you repeat this as long as you need, such that the data set becomes pure in the leaf node for each of these leaves. Now, how do you exactly measure purity? Well, there are different measures of impurity which we won't talk about here, but this was just to give a broad high level view for you, right? Now again, there are some issues like the k nearest neighbors that can happen for this algorithm also. One of the issue is how do you choose the depth, right? So how many times should you split the data set? Again, if you have outliers, what might happen is the outliers might make your data set impure. Now just to make sure that your data set is pure, you might keep adding more and more levels to this tree, and that might actually be wasteful, because just to fit the outliers you don't want to add too many levels. So you may want to stop your tree growing process at some point, and then say that, hey, I think everything other than this is impurity is caused by outliers. I don't want to grow this tree any further. Now how do you choose the depth of the tree? That becomes an interesting question. And how do you choose this purity, right? So again, as I have listed, there are two common metrics that people use: Gini index, information gain, and there are many other metrics that people use to measure impurity. Let's not worry about the definition of these things in this course. Just understand that there are different ways to measure how good a question is, and based on that your trees might slightly differ. And how do you decide as an algorithm which is the right measure to use is another question that one typically has to answer when working with decision trees. Okay, so to summarize, decision trees as an algorithm, you have this training data and you extract out a decision tree from this training data by asking most informative questions, splitting the data into two parts, and then seeing if the parts are pure enough. If they are not pure enough, you further split them on both sides till they reach your necessary level of purity on all the leaf nodes. And once they have reached, then in each leaf node you make a decision based on the majority decision of the data points left in that side. So now, which means that once you have extracted this tree, now you just apply this tree to the test data point. You ask the same set of questions, and as you ask the questions, you will navigate through the tree and you will hit some leaf node for the test data point, and that leaf node will have a corresponding label, and that label will be your final answer. So that is the decision tree algorithm, right?